because I had supercomputer problems yesterday. Getting to the point where I just had to do things on the board. It was such a pain in the ass. I am going to take roughly a 1 lecture break from our topic and do something that that has been identified to me as a weakness. And one of the reasons why it's a weakness is because many of you don't take quant. So I'm going to teach you a concept from quant that I think is important for you guys to have because it's really useful in the labs. And the first week of the lab kind of introduced you to the topic. And this week's lab, which is the ideal gas lab, you really need to use these skills. So today I'm going to talk about uncertainties and propagation of errors. All right. This is kind of an equation example class lecture. It's not going to be all that conceptually interesting, but these are really, really useful skills. And what we're going to come up with is an equation that allows us to calculate the error of anything given anything else. Okay. So let's just think kind of the idea of what we're doing in this class and how error propagation may be helpful. Right, remember that ultimately what we're trying to do in this class is to understand our box. And our box can always have a total energy, which is a function of some variables, right? And the variables that we're going to use a lot in this class are N, V, right? Sometimes we put entropy here, but we've introduced the idea of thermal equilibration, right? An isothermal bath, where we can now define things in terms of a temperature, right? But we can always write an energy in terms of N, V, and T. This has a very special name that we'll talk about next class. This is called an NVT ensemble, right? And this is kind of the box that chemists use to study things. So if you've ever seen studies of like people understanding how proteins fold and stuff like that, and do these really complicated calculations of proteins or DNA complexes and stuff. The box they build to do this what they call molecular dynamics, which is the box they build to let this protein relax with a bunch of waters and stuff. These are NVT boxes. So they fix the temperature, the volume, and the N inside the box, and they allow the system to equilibrate to some external bath. Okay, so this is a really, really important box, if you will, for chemistry. I'm just using it as an example here. I'm not going to really dig into this until next class. Next class, I actually have a computer program that'll simulate an NVT box for us. And we'll learn some things about how molecules or atoms exist in these boxes. Really nice, really cool little app you guys can play around with. And so we want to think it now, well, we want to measure the energy of our box. All right, let's go into the lab, right? And we want to measure U. So we can't measure U directly, but we know that we can always write U in terms of its variables. Right? So if we can measure N and V and T, there's some formula that allows us to calculate U. Okay, but the problem is that we don't always know N, V, and T very well. We might have some uncertainty to it, right? So for instance, let's say for instance we go into the lab, and this is something you're doing in lab this week, right? And let's say you measure the number of molecules in your box, right? You're doing this by feeding in this week, feeding molecules into your box, which is your flask, by using pressure, right? So pressure here is correlated in number because volume and temperature are fixed. So you're feeding in more pressure, that means you're increasing N, right? So your measurement of N, when you write it down in your lab report, you're going to write some average number, right? Imagine you do a bunch of trials. You fill it, empty it, fill it, empty it. That's what you guys did all class, or you're about to do. So you get some best value that you measure for N, right? The average value of N. Right. So this is your best average value that you measure of N. Right? Just do a bunch of trials, right? And I'll put this little bar on top of it to mean average. But there's some uncertainty to it, right? Because when you did your mass calculations you did in lab, you probably already learned that manual balance that you use to balance the flask away, it's not particularly accurate. It has uncertainty to it, some of which is systematic, as you'll see, or not all of it's random. And so we know that N has some uncertainty to it. Maybe it's a couple percent, maybe it's very small. But we can say very generally that this number varies between N and some error, which I'm going to call delta N, right? So this is our error. All right. I don't know what that error is. Often, maybe if you guys took statistics, we often think about averages and standard deviations or variances concept of standard deviation requires another assumption which we haven't made yet. But let's just say you measure n and you have a bunch of trials and they have some uncertainty, you know? And that's going to be delta n. Right? Okay, and then you can do that for all the other ones, right? So t is going, you're going to measure with a thermometer, and if that thermometer has some uncertainty to it, right? Now the thermometer uncertainty is really the accuracy of the thermometer, right? It's probably not an issue with you, but rather the thermometer itself. And volume, as you guys will find out in this class you haven't already, volume is kind of a hard thing to measure at times. Right? So your volume measurement is going to have some uncertainty in it as well. Okay, so I have three numbers that I measure, and I have some errors to each one. Now the question I want to ask is, given the error of my inputs, what's the error of the output? In other words, what's the resultant uncertainty of my U? Right, so what this means is that when I put these all in, my U value is going to be the U measured at the best fit values. N bar, V bar, T bar, right? That's what we measure, right? And that's going to have some uncertainty in U. Right? But we don't know what the uncertainty in U is. All we know are the uncertainties in our measurements, right? We're going to put that into our box, our formula for U, and get some number out. So we know this, but can we approximate what this is, given the uncertainties on the values? Okay, good question. What we're going to find is that we're going to come back to calculus here. Calculus is going to give us an answer for this. And it's going to give us a really general formula that allows us to calculate the error of a function, our output, as a function of the errors of our inputs. Okay, we can relate the two. So let's see how that works. So let's think about this. All right, so let's plot on a graph. Let's just look at one variable at the moment. All right, because I don't want to look at something in three variables. It's going to be really ugly. So let's just simplify it and look at one variable, maybe temperature. All right, let me make a coordinate system. Sorry. Ooh, that's a bad coordinate system. Sorry. Come on. There we go. Ah, beautiful. Okay, so what I'm going to do is we're just going to plot as a function of temperature, or whatever variable you want. We just pick one, temperature, versus energy. Okay, and so let's go ahead and measure our temperature, T bar, right? So that's our T bar. And we go look at the box and ask the question, right, what energy are you at? Right, and we get some value. The box says, hey, I'm at this energy. Right, and we'll call that energy U bar. Okay, so there's I'll make that point a little bigger so it's obvious, right? So there's my measured point. Okay, but T has some uncertainty to it, right? I've only put in the mean value of T, the average value of T, but T can fall within plus or minus delta T. Okay, so let's put some bounds there on T, right? So T can fall in any range between T, and we'll go T plus delta T. And equivalently on the other side, T can be minus that too, right? Plus or minus delta T. All right, so T can fall into any of these ranges here. And I'm just going to draw little vertical lines here. Sorry, my wrist is complaining, touching the screen. Right, so I know that T is going to fall within this yellow range. But likewise, U, depending on where T is, U is going to change as well, right? So maybe we need to draw a curve. How does U vary as T varies between these bounds? Okay, so let's go ahead and let's just say, for instance, that it looks something like this. It doesn't really matter. But maybe the function looks something like this. Okay, so what does that mean about the differences in U? Right? What are the possible values of U that may appear depending on our error? Well, it's going to be all of the values of u between the two bounds of t. So there's a minimum value that can be measured right here, right, at t minus delta t. So we can call that u minus delta u. And of course, there's going to be a possibility that t is actually on the higher end of the uncertainty range. And the u that we get from that t is u plus du. Okay. Right, so as t varies, u is going to vary. And how much u varies determines how much u varies as t varies determines how big du is. Right? So if dt is really small, then du correspondingly is going to be pretty small, unless u changes a lot along that range. All right? So what that means is that the rate of that the error in u has something to do with how u changes, the rate of u's change with respect to t. Right? So if t is very narrowly defined and u doesn't change that much along that definition, then du is going to be really small. Or if dt is really large, then u can vary a lot, and du is going to be very big as well. All right? So what I want to do is I want to find a relationship between du and the numbers that I've measured, dt and t. Right? I know these two. These are my errors, my experimental error. So I want to know how du varies as dt. All right, but that's what calculus teaches us, right? Calculus teaches us that we can calculate that for sufficiently small dt, that we can calculate the derivative at the point. Right? We can say that du is equal to dt, delta t, sorry, that's the wrong d.
Can you change the color, please?
I'm sorry? Oh, yep, sorry. Thank you, guys. Thank you. Let me change this all to yellow. Apologize for that. So du changes as dt changes. So let me do the little squiggly deltas because these are the errors. Oh, sorry, that's the wrong d again. I apologize. This one, delta, little deltas. T. And how do they vary? Well, they vary as the slope of the curve, right? The slope of the curve at that point, right? So this is equal to, du is equal to du, the derivative of u with respect to t, evaluated at t at the best point. Right? So we're going to calculate the derivative of the function at the best point t bar and multiply it by our error in dt. Okay? So what that says is that du is proportional to the error in t by the derivative, right? Our conversion factor. Just linearize it. Okay, so that's just for one variable, right? So that's really nice, right? This already gives us a relationship. If u is just a function of t, I'll show you this next class, but we're going to find out for an ideal gas. Here's an example. For an ideal gas, u is equal to 3/2 RT. For an ideal gas, it's 3/2 RT. So if we have some uncertainty in our measurement in t, what's the uncertainty in u? Right? So given our measurement t, which is t prime, or t bar, plus or minus delta t, delta u, the error in u, is going to be the derivative of the function with respect to t, evaluated at the point. Right, so let's go ahead and calculate that. Let me just get rid of these just for now, because we need some space. Right, so we have a function u is equal to 3/2 RT. So let's take a derivative with respect to t. What is that? This is a derivative of 3/2 RT with respect to t. It's a linear function. It's the derivative of a linear function, what?
3 halves r.
Yeah, 3 halves r, right? The t goes away. And that's multiplied by the error in t. Okay? So whatever our error in t is, we know that the error in u is going to be multiplied by 3 halves r. That's fixed. Simple as that. That's all it is. It's just a relative conversion between two different changing quantities. So you take a derivative. All right? So we always know the error of u is always proportional to the error in t by this proportionality factor. Okay. Really simple. Okay? Now, but the problem is, of course, is that u is not a function of one variable, it's a function of multiple variables. All right, so how do we take this idea and expand it to multiple variables? Well, we do exactly what we did when we talked about Gibbs's equation. When we varied u, we saw that the total change in u, du, is the sum of all the little changes in v and t and n and so on. Right? You get the temperature, the pressure, the work, chemical work, and potential, and so on. Right? We take partial derivatives of u with respect to those variables and see how u changes along each of the coordinates. Right? We're going to do the same idea here. So now take u being a multivariable function. And let's do the same thing, right? We're going to do the exact same process, same geometry, same Cartesian coordinates, right? But we're going to do it in multiple dimensions. And what we're going to get, right? So one option, so we can apply. So we're going to apply the same logic, right? And you would say, okay, well, if I apply the same logic, then that means that the error in u is going to be equal to the partial derivative of u with respect to n, right? Evaluated at the value of n that you measure, n bar, times the error in n, plus the same thing for the other variables, du dv, where v is set to v bar, times delta v, the error in v that you measure, was, sorry, these are little derivatives, sorry, these are du dn, these are partials, and du dt times delta t. Right, so you would say, okay, well, I'm just going to take the sum of all of them, right? And there's nothing wrong with that, right? This will give you an approximation for the energy, or for the error in u, right? Because it's the sum of the errors across each of the different coordinates. But it turns out that this overestimates the overestimates the area always. This is what we call a worst case scenario, right? This is the worst case scenario. As we'll see that this overestimates the error, so the straight sum overestimates the area, or error, sorry, and is considered worst case. Right? In some ways, the possible error for the system, for the energy, is no worse than this. This is as bad as it can possibly get. Right? So the question is, therefore, what is the, let's say, for instance, so this is the worst, this is the highest possible error that you can have. What's the average error that you can have? Right, so on average, what's the best possible case? What's the kind of best probable approximation of what the average uncertainty in u is? Not the worst energy, the worst uncertainty, but the average uncertainty. Right? And we just have to think about this geometrically. Right? And we're going to come up with a really nice, we're just going to take something from ancient math that will solve this problem for us very simply. And so here's the idea. All right, let's take a function of two variables. All right, so let's assume that u is a function f of x and y. All right, it's easier for us to do this in two variables than multiple because You'll see in a second, it's easier to draw it in two variables. All right, so I have values for x and y that I've measured. So let's say, for instance, here, this right here is the value x comma y. Okay, and then I'm going to displace this by dx. So this is x bar plus delta x comma y. Okay, so I've displaced my value by the maximum error in that value. So I'm doing a new point here in the energy space. All right, and then I'm going to do the same thing for y in the opposite direction. This point right here is x plus delta x with bars, and y plus delta y. Okay? So if this is f of x of y, and this is f of x plus dx plus f of y, and this one up here is f evaluated at the bounds. Okay, so what that means now is that the hypotenuse drawn from this right triangle, right, this is df. If this is dx and this is dy, then this difference right here is how the function itself changes, or the energy changes, as we go through the error bounds. Right? So what is the distance rule for this? It's not a straight sum, but it's Pythagorean. It says that dx squared plus dy squared is equal to df squared. So instead of taking a straight sum, we're going to take a sum of squares. Right? We're going to use Pythagorean theorem. Of course, in multiple dimensions instead, you're building these multidimensional right triangles. But really, the real relationship between the change in the function and the change in its variables is the sum of the squares of the changes in the variables. Okay, so let's just take that idea now, right, and bring back u of n, v, and t, go back to our original function. And what that says is that delta u squared, I'm getting my d's wrong, I apologize. Du squared is equal to the error in n squared plus the error in v squared plus the error in t squared. Okay, so instead of the straight sum, right, this is the error in n, this is the error in v, this is the error in t, these little terms right here. Right, so taking the straight sum of them, we're going to square each term separately and assume that the square of the final error is the hypotenuse of the triangle made by these errors. So what does that give us? It's okay if I go to the next page? I'll give you just a second if you want. All right, so let's just work that out really quickly. All right, so what that says now is that delta u squared is equal to the partial derivative of u with respect to, let's say, n, where n's evaluated at the value we measure, divided by the error times the error in n squared, plus the partial derivative of u with respect to v, where v has been evaluated at v prime, times dv, the error in v that we measure, squared, the uncertainty in v, plus the same thing for temperature. du dt, t evaluated at t prime, times dt squared. Okay, so what does that mean? Well, that means that the error in u is just the square root of this whole thing. Right, so that says that, so let me just kind of simplify that. Right, so here's the definition, the general definition of uncertainties for propagation of uncertainties. Right, when I say propagation, what I mean is I'm taking each of my individual errors and adding them together as squares. I'll give you a term for what that is in just a second. We have a nomenclature for this process. Propagation of errors. All right, so let's define it very, very generally. Right? It says if, oh, sorry, wrong color. All right, for a function, f, which is equal to a function. It's a multivariable function of variables a, b, c, and so on. All right, so you got a bunch of inputs, a, b, and c, with measured values of, and I'll write this in a different color, a equals the best value of a plus or minus delta a, b equals the best value that you measure of b plus or minus delta b, and so on and so forth. Right? That the error in f is equal to the square root of these derivatives. So we're going to take the derivative of f with respect to a. Here. Evaluate a at a bar times the error in a that you've measured in lab. Square it. And we do it for the same thing for b. We evaluate the derivative at b star, or b bar, multiplied by the error that we measure in b, and so on and so forth, forever and ever and ever. Okay. All right, so this is, again, this is just the Pythagorean theorem, just in multiple dimensions, right? It says that the error in f is equal, or the square of the error in the f is the sum of the legs. And the legs of error are the length, given an error, how much change in f, the length of that leg is how much f changes as you vary a. Okay. So we do everything with squares and square roots here, all right? So instead of linear sum, we do this kind of Pythagorean sum. And the term we use for this is a term that physicists and statisticians use for this. This is called quadrature addition. Right? When I say quadrature addition, that means that we're adding this, instead of summing numbers, we're summing the squares of numbers to get the square of the result. Let's do an example. I have a nice book on here. This is a really great book. I'll try to post a chapter of it if you want some more reading. This is written by a physicist, and it's literally an undergraduate book on this exact topic. And it's got some great worked examples and some really nice simple statistics. Very little math. This is the most complicated math it has. So let's do an example. Let's see, which one do I like? Okay, this is a good one. Well, before I do that, let me give you some formulas. Right? Because sometimes it's a real pain in the ass to calculate partial derivatives, and you've got to do it. If you have a big function, it's going to take a long time to do it. Right? So maybe we can simplify things a bit. So let's do some simplifications really quickly. And see how they maybe it's easier to use the simplifications instead of this regular formula. And then maybe it'll be easier to do an example. All right, so let's just think of some really, really simple functions that we can evaluate the errors on. All right. So let's do first, really, really simple, a function where that's just addition and subtraction. Okay, so let's say we're measuring something q. Right, this is the output, if you will, and q is just a sum of numbers. So it's a plus or minus b, plus or minus c, plus or minus dot, 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 dot. All right? And of course, we have, as always, a, b, and c are the things we measure. A has some error to it. B has some error to it, et cetera, et cetera. Okay? So again, what's the error in q? Right? That's ultimately what we want to solve. Right? We're adding a bunch of things together. What's the net error? Okay? But it's probably not too hard to think about this, right? We're just adding things. So it probably means the error in q is just the sum of the squares of the errors in each one, which is exactly correct. All right? So what that means is that the error in q is just the square root of the sums of the errors of each constant. Delta a squared plus delta b squared plus plus plus. Okay. It's not hard to get from here to here. Really, really easy. Because let's just do it really quickly. Really simple. We only do one term. Right? What's the derivative of q with respect to a? Well, this part's 0. This part's 0. It's got no dependence on a. There's only one term dependent on a. It's just a. The derivative of a with respect to a is 1. So this derivative is 1. 1 times delta a squared is delta a squared. Okay, so all the derivatives here just go to 1 and then disappear for addition. Any questions so far? Really straightforward, right? Not too bad. All right. We'll do something more complicated before the end of class, right? So make this more interesting. All right, I'm gonna mark this off. So this is how addition and subtraction works. All right, let's do something more interesting: multiplication and division. So times and division. Hopefully that's clear enough what it's making, times and division. Okay, so let's write q as a product and a quotient of some numbers. Right, same idea. Q is going to be, say, a times b times c dot 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 over x times y times z dot dot dot. Okay, so we got a product and a quotient. Now, there's an intricacy about this problem that we have to pay attention to. Is that imagine each of these numbers have units in them. Okay, so let's say, for instance, a is a length. Maybe b is a rate or a time. They have different units. Okay, so the question now is that when you calculate this sum of squares, like say, for instance, in this case, right? If you're adding numbers together, subtracting, they all have to have the same units, right? This has to be 1 meter, 2 meters, 3 meters. You can't add 1 meter to 1 second, right? That's meaningless, right? So in addition and subtraction, all the units are the same. Okay, so that means that each one of these errors all have the same units. Right? This is the error in meters, this is the error in meters, and so on and so forth. But over here, we don't have that luxury anymore, right? Because we can multiply a number in meters by something in seconds, or we could take a meter divided by seconds and get a velocity, right? Meters per second, right? So how do you compare, say, an error in meters to an error in seconds? How do you compare two different errors with different units? Okay. So for instance, let's just do an example. Right? Just kind of a thought idea. Let q be x over t, and x is 1 plus or minus 0.1 meters, and t is equal to 1 plus or minus 0.2 seconds. Okay, I'm gonna clean that t up for you. Right, so the question that I have to ask now is, which one is more poorly defined? Right? How do I compare this error in meters to this error in seconds? Okay. Now, we can do a really simple analysis of this, right? We say, okay, this number is going to range between 1.1 and 0.9 meters, right? So it has about 10% error, right? And then here you say, oh, this one has 20% error. Would you all agree with that statement? This is a pretty straightforward claim, right? But what math are we doing there by saying that? Right? You logically say this has 10% error, this has 20% error. Right? So that would mean t is more poorly defined, right? You've just made that calculation in your head. But what have you done to do that? Well, you've compared these numbers in a way that's unitless, right? We're not measuring, we're not thinking about the error in terms of the unit, we're thinking of it in terms of percent, right? That's a unitless thing. It's something we can compare. We can compare units and fractions together. Right? What's the fractional or the percent error of each of these that's possible? How well do you know them to a percentage? All right, so what we're going to have to do is take each of our values and make them unitless, to think about the fractional or the unitless error of the term. It's really easy to do. I'm going to introduce now the really kind of very useful thing, the definition, fractional error. For a value, let's say x plus or minus delta x is the absolute value of delta x over the value of x. I'll make that bigger so it's better written. Sorry, guys. So you take the error and divide it by the value that you measure, that's x hat, and this is what's called the fractional error. Right, so let's just quickly do the math, right? So what's the fractional error over here? Right, so delta x over x, absolute value, is 0.1 over 1, which is 0.1, right? And if we multiply that by 100%, right, that's 10%. Right? 10% or 0.1 fractional error. Right? And just like with t, we have 0.2 over 1, and that's 0.2, which is 20% error. Okay? So notice that I've gotten rid of the units, right? X, dx and x have the same units, so when I divide them, those units go away. So fractional error is a way for us to objectively compare two different observed values and see which one's more precise or not, right? The contribution of its error. That being said now, if this is the thing we have to think about, then we're also going to have to calculate, what we're going to calculate is the fractional error in Q. Right? So if we're going to compute our errors by fractions, then the output's going to be a fraction as well. Right? So by doing that, what you get now for a multiplication is that delta Q over the value of Q that you measure, absolute value, remember errors are always absolute, is equal to the sum of the squares of the fractional errors. So this will be dA over A, absolute value squared, plus the error of B over the value of B, absolute value squared. And you also, in this, get the denominator as well. So we get dx over x squared, and so on and so forth. Okay, so there's really no difference whether it's in the numerator or the denominator. Okay, so when you have numerator and denominator and you propagate the error, you're just going to add all the terms together. Okay, like this, but you have to use the fractional error because all the numbers may have different units. I put the absolute values there, but when you square something, it's always positive, so you don't really need the absolute value. You just square it, right? Just to be safe. Square is always positive. All right, you already have all you need to do. This is every equation you need for this week's lab for the error analysis, right? Because you're ultimately doing PIV-NER. And all PIV-NER is a product and a division, right? So this equation, you just replace, here maybe, I think you're measuring n, the number of moles, right? You would have dn over n, and it would be the sum of the fractional error in P plus the fractional error in V plus the fractional error in T, and so on and so forth. Why don't we do a problem? All right, this should help you guys, actually. Is it okay if I keep going? Next page? Okay. Cool. I got plenty of time. Excellent. Very good. All right, so let's just do an ideal gas law problem and calculate the uncertainty. Okay. Just like what you're doing right now in lab. Okay. So what we want to measure is the number of moles of our gas given a pressure, a volume, and a temperature. I don't say R because R is a constant, right? All right? So I want to calculate the uncertainty in N. Right? So what's delta N? Okay. So delta N, right? We're just going to use the multiplication equation. Delta N over the value that you measure for N. Of course, N is always positive, so I don't really need to write the absolute value, but just to be safe, is going to be the square root of the sum of the squares of the fractional errors of the variables. So that's going to be the error in P divided by the value you measure for P squared plus the error in V divided by the value you measure for V squared plus the error in R divided by the value that you measure for R squared, and then the same thing for T. Okay, so let me write down some numbers. We need to measure something, right? So we'll measure P. So P we measure to be 1.00 plus or minus 0.01 bar. All right, so basically an atmospheric pressure. We'll say the volume of our container that after we measure of water is 2.10 liters, plus or minus 0.01 liters. And the temperature, as you guys probably saw, you can really only get to 1 degree, plus or minus 1 Kelvin. Okay, at R here in these units is 0.083144 liters per bar per Kelvin per mole. All right, that's the ideal gas constant for liters and bars. Okay, so all we have to do now is just plug and chug, right? But we need to calculate a few things first, right? First, we need to figure out what is the value of N do we measure? Right, the denominator here, right? N is the value that we measure with the values of V, P, and T that we measure in experiment, right? I'll call this P, V, T, and R. Okay. So first we need to calculate N, right? We need to know what the value of the moles that we get is, right? So all we have to do, that's really easy. N is the value of P we measure divided by the value of R we measure. R times T divided by R times T. Okay, and so that's just a little plug and chug. Right, this is 1 bar times 2.10 liters divided by this big ugly number, 0.083144 liter per bar per Kelvin per mole. Times 298 Kelvin. Right? So those are all the measures we measure. Let's make sure the units work. We should get moles out. Right? This is always a good test in this class. We do a lot of things with units. So if you know what the expected units are of your result, when you do your unit analysis on your calculation, you should get the same units out. It's a really good way to tell if you screwed something up or not. Because if you don't match, the units don't match, then you know you've done something wrong. So what do we got? We got liter bar. So we got liter bar in the numerator. We got liter bar in the denominator. Those cancel out. We have a Kelvin in the denominator here and a Kelvin here as well. So those cancel. So the net units are 1 over 1 over mole. And that's just mole, which is n. All right, the units all work. The only thing that's left is mole, 1 over mole to the -1, which is mole. So we're good? That all works. And again, it's really easy. This is 0.0848 moles. Okay, so that's what we measure. Right? That's our best guess value for n. But what's its uncertainty? Right? Well, all we have to do is plug it in. Right? We have all the values that are on this equation for the uncertainty. We just need to put everything in and solve for dn. Right? So dn divided by the value of n we measure, which is 0.0848 mole, is equal to the square root of, let's do the pressure first. So that it's the uncertainty of the pressure divided by the value of the pressure. So that's going to be 0.01 bar divided by 1.00 bar squared. Now we do it for the volume, 0.01 liters. That's the error in our volume, divided by 2.10 liters. That's our volume squared. And then we have this term delta R over R. Now R is a constant. It's defined exactly. So there is no delta R. This term is 0. Right? Because R is a constant. Right? All constants are defined to have 0 uncertainty. Well, most of them. Everything in this class has. Every constant in this class has 0 uncertainty. Right, so that goes away. And we're left with the uncertainty in T. And that's going to be 1 Kelvin over 298 Kelvin squared. Okay. Now look, notice, let's see if the units work. Right? Delta N has units mole. This has units mole in the denominator, so there's no units here. The bars cancel, the liters cancel, the kelvins cancel, everything's unitless. This is unitless error, fractional error. It's independent of the unit. It's just a relative measure of quantity or magnitude, if you will. Right? So let's set that equal. What is that equal to? Well, I got to multiply both sides by 0.0848. And so I'm going to multiply this by 0.0848 and multiply this by 0.848. I just want to get rid of it. Moles. Just multiply both sides by that to get rid of it. Right? And delta N is equal to 0.000981 moles. Okay, so that's our error. So what that says now is that our value, our measured value, our experimental value for the number of moles in our gas, which is the best value plus or minus delta N, is equal to 0.0848 plus or minus 0.000981 mole. Okay, so let's look at this a little more carefully, right? That's not really the best way to write this. It's kind of ugly, right? Where does the error come into play? What's the first uncertain digit in this number? Well, the first 3 digits have no error in it. So the first digit that has error is the next one. So this has no error, this has no error, this has no error, this has error on this digit. So we know at least we have 3 significant digits, because these all have 0 error. So there's a couple of different ways to write this. And you're welcome to use whichever one you like. I'm just going to give you some options. So one way to write this, so different ways, different expressions, different ways to express. All right, I'm going to go in terms of increasing elegance. Of course, the least elegant way, the CHEM way, is to write 0.0848 plus or minus 0.0009 mole, right? Because the first digit that's uncertain is the fourth. Okay, so that's one way to write it. That's how significant digit rules would tell you to do it. Something slightly more elegant, we'll call this majors chemistry, would be to write this in scientific notation. This would be 8.48 plus or minus 0. Let me think about this. 8.48, 0.09 times 10 to the minus 2. We often put it like this. One way to write it. And then the official way to write it, and by official I mean federal government, the Department of Commerce, National Institutes of Standards and Technology, the NIST method. This is the official method of the federal government to display errors, is to write your significant digits such that you have 2 digits of error. So we want to write this number so that it ends so the error is at 9/8. Okay, so how would that look? So we can do it in scientific notation if we want. I'll give you 2 different options. Right? So one way to do it would be 0.08480. And then the error in those last 2 digits is 9/8. All right, so what does this mean? This is what's called the NIST Type 1, Type A method of error reporting. The error is put into parentheses, and it's the error on the digits next to it. Okay, so we have 0.8480, right? And we have 98 units of error on the last 2 digits of the number. So what this means is that, so this is what? The tenths place, the hundredths place, the thousandths place, 10,000ths, and the 100,000ths place. This means we have 98 10,000ths of an error. Right, so this value will vary 0.084, 80 plus or minus 0.00098 or minus 98. Right, so this 98 modifies the points at this decimal, if you will. Right, so this number modifies at this place an error. This one modifies this one. Okay, and another way to write that would be with scientific notation, which would be 8.48098 times 10 to the minus 2 moles. All right, on the next homework, I'll give you some practice with these. Okay? All right. People tend to have a little trouble getting used to this, okay? So I'll give you some exposure to it because everyone uses it. It's pretty much the standard professional way to report errors, certainly in the federal government and most physical science. Okay, very simple, right? So this is all you're going to do in lab. Now this week you've recorded a bunch of deltas for all your variables. You have all these uncertainties. You have trials that you can average to calculate your bar properties, your V bar, your mass bar, and so on. And all you have to do is propagate the errors out with this formula. Okay. Any questions? Cool. Let's do one more tricky problem. Okay, I like this problem in the book. All right, it's a little bit of a physics problem, but I think it's relevant. All right, so let's say, for instance, we want to find, we have a motor. An electric motor that drives, what are we doing here? That drives a a pulley. Let me clean this up a bit. It drives a pulley. We have a pulley here that rotates. So as the motor rotates, the pulley rotates, and connected to that pulley is a mass M, right? And we want to measure it. We want to lift it by a height h. Okay, so we want to take this mass and we want to use the motor to raise it by a height h. Okay, and I want to ask what the efficiency of the motor is. What that means is for every unit of energy the motor creates, how much is being used to do work, to lift the motor, or to lift the mass. The reason why we ask this question is really fundamental. Because if you think about, for instance, of all the energy your car engine, who here drives, anyone here drive an electric car? Okay, so literally, who here drives a car? Okay, so literally everybody in the room. So you put in your gallon of gas and it creates an equivalent amount of energy per gallon of gas. Do you guys have an estimate? Do you have an idea how much? So let's say it generates X number of joules of energy that you can use to drive your car. Do you guys happen to know how much of that energy is actually used for driving your wheels? Anyone have a guess, percentage-wise? Throw a number out. What do you think? Curious what you guys think. Yeah, go ahead, Desmond.
Yeah, like 65.
If you made a 65% thermal efficient combustion engine, you'd win a Nobel Prize. You would literally change the world. I went to a talk a couple years ago from a researcher at Hyundai, in their combustion analysis department. And they just developed an engine, a new car engine that they're developing for hybrids that hit 51% efficiency. So what that means is for every 100 joules it creates, only 51 is used for actually driving the car. The rest is generated as heat. It's thrown away. Right? That's really good. Most of your cars run, like for instance, I calculate for my Honda. My Honda's about 37%. All right, so 2/3 of the energy is completely thrown away. Okay, so efficiency for motors is really important. Now for electric motors are much more efficient. Like a Tesla motor is like 80% efficient or something like that. Okay, so every 80% of the energy is actually used to drive the wheels, and most of that loss is friction. Most of the loss is friction. So it's important to think about the efficiency of the motor, right? How much energy, right? That's important because you got to spend money for electricity. You want to use as much of that money for work as possible. So we're going to write the efficiency of the motor, which is E. Efficiency. How much time do I got left? Okay, good. I got plenty of time for this calculation. All right, and that's going to be, and we'll actually look at this for chemistry very soon. So we'll do the work done by the motor. The efficiency will be the work done by the motor divided by the total energy used, total energy delivered. Okay, and this is a DC electric motor, so it uses a current. Right, so the source of the energy is not chemical, but rather electrical. So we've got a wire, we've got some wire in here going in, right? This is our electrical input. Right, our energy is going in this way through a wire. Right, we're feeding voltage into it. Okay, and I'm not going to derive the equations here, but it's not too hard. The work done by the motor is the gravitational potential energy of an object at height h, which is just the mass of the object times the gravity, the acceleration due to gravity, times the height, mgh. Right, that's the gravitational energy of an object. And the energy, the energy delivered to the motor is the voltage of the motor times the current times the amount of time the energy is delivered. All right, so let me just write that. This is V is current, voltage. If you don't remember this, V is voltage. I is current. And T is the time motor runs to lift it. Okay, and what is, does anyone remember the acceleration due to gravity, g? Do you know the number?
9.81.
There you go, 9.81 meters per second squared. Yeah. Or at least learn one thing from physics. Did you guys know that this number varies around the Earth? There are places on Earth where it's lower and higher by about 1%. It's really cool. Someone actually did that. They took a satellite and they measured the gravitational potential of the Earth. And there are regions where the Earth is less dense, it's directly down than others, and there's places where there's less gravity than there are in other places. I'll also try to find a picture of that. Okay, so let's do some, I'm just going to kind of do the suppositions of this problem, okay? So let's just say first that, which is very general, that M, H, V, and I can all be measured to 1% accuracy. Okay? And let's say that time is 5% accurate. The reason why time may not be accurate is because there might be other conditions, such as temperature, that may affect how long it takes for this thing to raise. Right? If there's temperature is high, maybe friction is high, maybe a squirrel got in and got some nuts and it's just kind of grinding and it's slow. Right? So T may vary a little bit because of conditions. Okay, so now the question is now that we know all the errors, right? What is the uncertainty in our efficiency? All right, so let's look at that carefully. All right, remember, so we have a formula that's a bunch of products, right? Product and quotient. So we have to use fractional errors, right? So that means therefore, right? That means that the error in E divided by E, right, is going to be some sum of the different errors. Let's do both ways. Let's do the linear addition and then the quadrature addition and see how it changes. So first, let's say that, for instance, it's equal to the error in M divided by M plus the error in H divided by H plus the error in V divided by V plus the error in current divided by current plus the error in T divided by T. Okay, so this is our kind of worst case, right? This is our worst case. Right? And so how do we evaluate this? Well, we know the percent accuracy, so we know all the fractional errors, right? 1% accuracy means a 0.01 fractional accuracy, fractional error. Okay, so that means therefore that we have a 0.01 for M. And I'll just write it so we keep track of them. This is M. We have 0.01 for H, 0.01 for V, 0.01 for I, and 0.05 for T. Okay, so we add those all up, right? It's just simple arithmetic. We got 1, 2, 3, 4 plus 5, 0.09. Which is 9% error. All right, so by adding the errors, we approximate that we can only know the efficiency to 9%. Okay, so what about if we do it properly? Right? This, as I said, this is the worst case. Right? So we should technically, on average, be doing better with our certainty on H, or on E, excuse me, because we need to take some square roots. Right, so let's try that again. So let's do that in quadrature. And it says that the error in E, the fractional error in E, is equal to the square root of each of those. So I'm just going to write them in, right? We have 0.01 squared plus 0.01 squared plus 0.01 squared. We have 4 of them. plus 0.05 squared. Okay, I'll let you guys can run that calculation. Again, it's really easy. What you find is that this ends up being the square root of 0.29. Sorry, 0.29. I forgot the error. So it's 0.29, right? Which is approximately 0.05, right? Which is 5% error. All right, by doing it properly, we've reduced the uncertainty in our numbers by 5%, right? And what does this mean? Right, so what's the difference between these two approaches? Okay, why is it that when we do it not wrong, there's nothing wrong with this, it's just a really, really conservative estimate, right? This is what you do when you're like, I'm pretty sure it's going to screw up, so let me give you the worst error possible, right? And so what's happening here? Well, what's happening here is by assuming a linear addition, you're assuming that every value of each of your measurements are on the edge of the measurement range. Right? So this is assuming that m is not actually at the value you measure, but it's actually at delta, m plus delta m. It's on the edge somewhere. Right? So these all basically add up and propagate the uncertainties that are worst case, which is that you are literally as statistically far away from the correct answer as possible. Statistically allowed. Right? So this is the sum of all the statistical extrema, if you will, for each of the values. And so likewise, your uncertainty is going to be very large because of that. Because all of these are off by the maximal amount that they can possibly be by the statistics. Here what I'm doing now is I'm taking averages. I'm saying that in these cases, that my values may deviate from the actual error, from the actual value. My measurements may deviate a little bit, but on average, they're within one standard deviation of the correct answer, right? They're right kind of within plus or minus. They're within that like little 60% certainty range that you learned in statistics, 67%, right? So we're, in this assumption, we're assuming that all of the measured values are kind of right near the middle, right to the mean of the range. Right? So this in some ways is the average uncertainty, given that we have average results for our measurements and we haven't screwed them up really bad. Okay? We're assuming everything is measured and is kind of random, and we're making good measurements and we have good uncertainties, and we expect that the value, the correct value for each of the variables is right roughly where we measure it. And that'll bring your error down by about a factor of 2. Okay? So this is truly worst case. This is saying that you did an okay job figuring out the uncertainty of your variables, but you did a really bad job measuring them because you're on the edge. And here you're assuming that you're doing an average job measuring them. So in this class, we're always going to be taking averages. We want to think about averages, right? Everything is going to be an average. When we see on Thursday, I'm going to show you that for real. It's that thermodynamics, that's entropy, are just averages of things. And so it's really important that we kind of keep ourselves in this idea of sticking around averages. And this gives us a nice, reasonable estimate for our uncertainty. All right, what time is it? Any questions? Okay, I don't want to say I'm done yet because I have one more thing to say, but I don't have any other further work to say. So what we're going to do with this is, again, on Thursday we're going to come back into thermodynamics again with a more statistical mindset. All right, I want to start thinking about errors and uncertainties and fluctuations, right? That not everything is as well defined as we expect it to be, right? And I kind of want to see how thermodynamics evolves from that perspective, all right? The perspective of randomness and uncertainty and statistics, all right? So I'm going to try to connect these statistical ideas back to what we've been talking about, in particular entropy, about the statistical nature of entropy and how entropy plays a role in these statistics and uncertainties. And that'll allow us to really kick back into full swing with thermodynamics next week. Okay, guys. Have a good one. I'll see you on Thursday.
I have a question.
Yes, ma'am.
Because I know I have people coming tonight, and I expect that we'll get to problems.